Okay, so these simple harmonic motion problems are, we're not going to look at too many that are that complicated, but it does take a little bit of experience to visualize what's happening here with some of these. So it says an object is attached to a coiled spring. So what we can assume then is there's some sort of, platform, let's say, and if the weight is attached to this coiled string, I'm not going to draw a curly Q thing here. I'm just going to draw a string with a weight attached to it like so. Okay, now again, this is sort of a spring action, right? We have to think of it that way. The object is pulled down in the negative direction from its rest position. So let's say this is its rest position, okay? And the object is pulled down to here, okay? So right now this string is or the spring, I should say, is very stretched out, ready to snap and recoil back, right? Okay. It says that is a maximum 7 centimeter displacement here. So this is rest, okay? 7 centimeters below that, it's pulled down, and that's where this motion starts from. And then it's released. It takes 2 seconds for the object to reach its maximum displacement above rest position. So what's going to happen when you release that weight that's on a spring, it's going to recoil. So that weight is going to shoot past its rest position and up to its maximum displacement up to here, okay, which is also 7 centimeters. So the way that we can visualize this in terms of, the motion that we've talked about is this is a question about displacement in time, right? So we have an x-axis and a y-axis. Now we've been looking at, we've been thinking about sine and cosine waves for a while here, and we've been looking at this. So our x-axis, this is our time, as it typically is, the independent variable. And the y-axis here, this is our displacement, okay? So at the beginning of time, at the beginning of this trial, right, the object is 7 centimeters below its resting value, right? The resting value, this is really its equilibrium point, okay, which as we typically say, is the x-axis for a wave. So starting at a maximum displacement of 7 centimeters, and then as time goes by, it reaches its maximum displacement above. So, right, it's shooting straight up, right? And gravity and movement thus is not necessarily linear here, but it comes up, it passes its rest position, and then reaches its maximum displacement after 2 seconds. So this distance is 2 seconds, right? And then because it's simple harmonic motion, it's going to then recoil straight back down and end up at a displacement of 7 seconds here. So we can say that half the period is 2 seconds, right? The full period would be 4 seconds. So it takes 4 seconds. If it takes 2 seconds to come up, it would take 2 seconds to come back down. So the period is 4 seconds, okay? The maximum displacement is 7 centimeters. That's our amplitude. When we go to write this function, the distance or the displacement in terms of t, okay, you've got to decide if you're going to use a sine or a cosine wave to explain this, right? At this point in the game, you should realize that when an object is at a maximum displacement at the beginning of the period, that can be modeled by a cosine wave. In this case, it's a cosine wave that's been reflected over. So the amplitude is 7, but we're going to say -7 cosine. And then the value we're missing is omega, right? And so we used to call it B, now we're calling it omega, but it doesn't necessarily affect it one way or the other. 4 is equal to 2 pi over omega. And then we pull the switcheroo here and we say omega is equal to 2 pi over 4, which is pi over 2. So we have pi over 2t inside this cosine function, okay? So really the trickiest part is kind of trying to visualize this, understanding that there is positive and negative displacement involved when you think about where that equilibrium value is, and understanding how to find the period and amplitude, because really those are the only two variables in simple harmonic motion. The one effect that we can have is that negative value of something starts low, or if it starts at equilibrium and then goes down, that would be a reflected cosine wave. Okay, so keep that in mind when you're coming up with these functions.